All right, so we're going to start off by reviewing kind of what we know already about energy. Oops, we're going to keep the paper. All right, so energy. There are two very, very, very basic types of energy. You can have mechanical or non-mechanical. When we talk about non-mechanical, examples would be like solar, nuclear, that kind of thing. Yes, a windmill would be. Well, it kind of depends because a windmill takes the solar or the wind energy and turns it into mechanical energy typically, or chemical energy that we use for mechanics, but there's a lot of crossover here. All right. But really what we're concerned about today is the mechanical. So there are two types of mechanical. The first type is mechanic. Try that again. The first type is kinetic. What does kinetic energy have to do with? Movement. All about that movement. The other general form of mechanic energy is potential energy. And if kinetic energy has to do with movement, potential energy has to do with kinda, it's about its position. Just stop it. Thank you. All right, potential, you have two types. You'll have elastic, which we talked about with Hooke's law, and gravitational. When we look at these formulas, elastic, we use U sub S, us, and for gravitational, we use U, G, UG. Questions so far? So I'll kind of review what we know. So today we're going to talk about the conservation of energy, which I know all of you know. In fact, when I start writing it, most of you are going to finish it without even having to look up because you know it. So conservation of energy. Conservation, of course, means to save. And when we're talking about conservation of energy, really what we're concerned with is the first law of thermodynamics. The first law of thermodynamics says that energy cannot be created or destroyed. It can be what? Transferred, transformed. So, energy cannot transformed. Okay, an example of this would be like if you had solar panels on your house would be powered by the sun, but the sun's not creating that energy. The sun's releasing the energy stored in the nuclear bonds of the hydrogen atoms that's released when they fuse together to make helium. The sun releases all that energy. Our solar panels pick up that radiation and use it to power our homes. Okay, so the sun's not making energy. It's releasing energy already stored. Yes?
Would our paper have energy? Just being paper?
Mm-hmm. And you can release it. I wouldn't. I don't think it's digestible at this point. So our first equation says basically the total mechanical energy. The total energy is equal to the kinetic plus the potential. Now, I will tell you, you could have a problem that has both types of potential. In level physics, it's not going to be seen really much at all. It could. You could solve it. It's actually not that much more difficult. But we typically stick with just gravitational and kinetic. The other equation is the mechanical energy that you have initially is going to be equal to the mechanical energy you have final, which is just a fancy way of saying whatever you start with, you finish with in a closed system. If you have 3,000 joules to start with, at the end you still have 3,000 joules. If you have 2 joules, you end up with 2 joules. When I say closed system, remember, I'm talking about like there's no interference from outside things. Nothing's coming and adding energy in or pulling energy away. It's closed off. Doesn't really happen in a real world, but to study the fundamentals, you have to understand it's in a closed system. So, this first problem about the pendulum. Pendulum has a mass of 0.2 kg, reaches a height of 0.01, and a max velocity of 0.45. What's its total ME? What's its total mechanical energy? So it wants both forms of energy. You can solve for either one first. I like potential better because I don't have to square anything, so I'm going to solve for that first. So remember, our formula is UG equals MGH. Point 2, easy gravity of 10.01. Watch your decimals when you're entering this in on your calculator. But go ahead and solve it for me, please. .02 joules. Okay, we're going to do the same thing. We're going to solve for kinetic. Kinetic energy is equal to 1/2 times mass times velocity squared. I'm an adult, and one of the things you can decide as an adult is not to deal with fractions, so I don't. So I'm a 1/2, which is 0.5, times the mass of 0.2, times the velocity 0.45, and that has to be squared. Yep, so with some rounding, 0.02 joules. They don't always work out this way. Honestly, I picked these numbers at random. I'm not quite sure how I managed, if you want me to be completely honest, but here we are. So my total mechanical energy, my total energy is going to be my potential plus my kinetic, which would be 0.02 plus 0.02. What does that give me? 0.04 joules. That's it. This is why we spent so long making sure we were good on potential energy, making sure we were good on kinetic, because we were going to put them together eventually. A 0.07 kilogram air hockey puck has 5 joules of kinetic energy. What velocity will it have after traveling 1 meter down the frictionless table? How much kinetic energy do I start with? 5 joules. How much will I end with? 5 joules. Okay. So I know at the end I'm going to have 5 joules of kinetic energy. And I want to find that velocity. So I'm going to put in my kinetic energy formula. So this becomes 5 is equal to 1/2 times my mass times my velocity squared. Okay. This is why I don't use fractions, because a lot of you will just try to divide the other side by the fraction and you have to flip it and all that junk. So we're just going to do, please excuse my dear Aunt Sally, and we're going to multiply and get rid of our parentheses first. So what is 0.5 times 0.07? 5 equals 0.035 times my velocity squared. Okay, now I have to get my letter by itself. I have to get velocity by itself. How do I move 0.035 to the other side?
Subtract.
To move something across the equal sign, you have to do opposite of what it's asking you to do now. So this is saying 0.035 times. So I'm going to divide both sides by 0.035. 5 divided by 0.035, it gives you a number that's pretty high. I'm rounding to 142.9. Is going to be equal to my velocity squared. How do I get rid of my squared? Square root that number. When you square root that number, you should get 11.9 meters per second. Make sure you are taking your time not to make stupid algebra mistakes, because you know what you're doing. We get a little cocky. We just, whoop, gonna get the answer, and I'm going to subtract. I'm going to multiply. I'm going to take your time and give yourself the opportunity to do what you know what to do. Either underneath your notebook, underneath your warm-up today, or on the back of this page, kind of depending on your lifestyle, I'm going to give you some numbers. I want you to see if you can't solve for some things. If I have mechanical energy of 1575 joules and a mass of 12 kg and a potential energy of 1265 joules, I need you to find my kinetic energy, my velocity, and the height. I'm going to zoom out. Take a minute. See if you can't figure out. I'm sure a lot of you wanted to just use the kinetic energy formula, jump right in there, solve for kinetic energy, right? I didn't give you enough information for that. But you do have that. So to solve for kinetic energy, you've got to do opposite of plus, which is subtract. Now you can solve for your velocity. Be 310 equals 0.5 times 12 times velocity squared. Which should simplify down into 310 equals 6 times v squared. And when you divide 310 by 6 on both sides, you should get something around 51.7 for your v squared. And then square root that, baby. 7.2 meters per second. All right, and the last thing I asked for is height. It's going to be m times g times h. I gave you the potential energy of 1,265. 12 times 10 times height. I have to divide both sides by 120. Which should give me 10.5 meters. Any questions about that? Actually, here's a quick video.
With their high speeds and bright colors, you may find it hard to believe that roller coasters have been around for more than 200 years. But since their beginning, the basic science behind roller coasters has remained the same. It's the science of forces, energy, and motion, called physics. Like any other amusement park ride, roller coasters need energy to work. But it's what happens to that energy that makes roller coasters unique. First, the cars of a roller coaster are pulled to the top of a steep slope by either a chain system or another machine for pulling and lifting, called a winch. These machines need energy to work, but this energy doesn't just disappear. It is changed and given to the cars of the roller coaster. What is this energy changed into? And how does it go from the winch to the cars? An object sitting still at the top of a hill has stored energy due to its position. This position gives it the chance or potential to move down the hill, and so we call this stored energy potential energy. As the cars of a roller coaster are pulled up to their starting position, they are gaining potential energy. The higher the cars are pulled, the more potential energy they gain. And once there's enough potential energy, the fun begins. As the coaster cars zoom down the track, their potential energy is turned into another kind of energy. If potential energy is the energy of position, what do we call the energy of motion? Kinetic energy. Both this potential and kinetic energy rely on a fundamental force of the universe, the force of attraction between all things that we here on Earth feel most strongly as the downward pull of gravity. When roller coaster cars go over the top of the ride's first hill, the force of gravity pulls them downwards, turning their potential energy into kinetic energy. And as the cars climb the next hill, the kinetic energy is turned back into potential energy, which is then released again as kinetic energy, and so on. Alternating between these two types of energy makes for an exhilarating ride. Now the next time you ride on or see a roller coaster, whether just going up and down hills or spiraling through turns at 60 miles an hour, you'll know a little more about how physics is turned into fun.
Okay. So that video is just kind of showing us how the total energy gets transformed into kinetic and potential. There is friction, there is thermal energy, but again, we're not really dealing with those right now because we're dealing in a closed system. We're not going to talk about those. You should have picked up a conceptual physics. All right. This is one system. Okay, a ball at this height has 30 joules of potential energy. So what is it going to have at the same height? 30. And here? Okay. In these cases, there's no kinetic energy. It doesn't indicate movement at all up here at the top. So we can assume that the total energy for this system is going to be 30 joules. So if this ball were to go from here and fall down here at the very bottom when it lands, what's its kinetic energy? 30 joules. Okay. It took 3 steps, 1, 2, 3, to get 30 joules. What would the potential energy be at 2 steps?
20.
And it doesn't ask for it, but you would assume then that that ball's moving down those stairs and it has a kinetic energy of 10. Pretty simple, right? Okay. Our little vroom vroom car. We are going to talk about this again and again and again. So if for some reason today it's not sinking in, we're going to put it a different way tomorrow, so no panicking. I have a velocity of 30 and I have kinetic energy of 10 to the 6 joules. If I increase my velocity to 60, what did I do to do that? How many times?
You increased it by 30.
I increased it by 30, so how many times would that be?
Maybe 10 to the 7.
That's a good thought. But to get to 60, I really doubled my speed, right? So I doubled my velocity. Now remember that my kinetic energy formula, my velocity gets squared. So I have to square my velocity. And so what we see is that doubling the speed quadruples the kinetic energy. Is 2 squared is 4. So it'd be 4 times the original kinetic energy. Okay, I know. I said it was gross. We're going to revisit it. It's not a big deal. We're going to do it again.
So next one, what does it say?
4 times 10 to the 6 joules. So again, going back to our 30, how did I get to 90? Multiply by what?
4.
3. 3 times my initial velocity of 30 would get me to 90. And since I'm looking for my kinetic energy formula is squared. I've got to square this. What is 3 squared? 9. So this would be 9 times 10 to the 6 joules. On this one, because we haven't really talked about work yet, that's the next unit. I want you to change that to kinetic right before it hits. And y'all can figure that one out. But I want to look at my diver. So just change that to kinetic. My bucket diver. Very sad movie about that made in the early 90s. It's very, very, very sad. It had a horse in it. And I cried. She goes blind. But this dude has 15,000 joules of potential energy at the very top. Does he have any kinetic? No. So what's his total mechanical energy?
1,000. 15,000.
15,000. Okay. This is a closed system. Stay with me here. So that means at every point among his path, and he has great form, by the way, the total energy will always equal 15,000 joules. So right here where he flattens himself out, I would go ME equals KE plus UG. I know that's 15,000. I don't know what my kinetic is, but I know that that's 11 to 50, and I would subtract them to find my kinetic energy. And I would do that all the way down. You will see that this is the same concept, and this down here with my pendulum is the same concept. You now have everything you need to know to be successful in that. Good luck.